Okay, so thank Capini for the invitation.
It's from everybody.
Here. So I'm going to tell you something about the atypical growth in a random interface. But first, I want to tell you the atypical growth is just some fancy name for, what I'm going to talk about is the large deviation principle, and the random interface underlying it's a stochastic partial differential equation. So I'll focus on two types of questions. One question is understand the probability of rare events. So again, the method behind is the large deviation principle. And the other one is the consequence after a rare event happened. It corresponds to some limit shape. So it's important to understand these two questions because, okay, although we are facing rare events, things like car crashes, but it can have very serious consequence. And since in the example of car crashes, there are many people driving a car in the same day. So although, the probability for each person to get in crash, it's low, but there will be some crashes happening every day. So it's important to understand the probability behind. And also when the car does crash, then we want to try our best to reduce the casualty. That's why we ask everyone to put on the seatbelt and things. So it's important to understand the consequence after a rare event happened. So we'll study these questions for a stochastic partial differential equation that models the random interface growth called Kadar-Praising-John equation. And to explain the philosophy and the method behind, let's first explain through an example using Brownian motion. Okay, great. Yep. So I will use W to denote the Brownian motion on time interval from 0 to 1. And what I consider is I multiply it by a small parameter root epsilon. So when I let epsilon goes to 0, so if you look at this random trajectory in time 0 to 1, then you will just converge to 0 in probability. So what the large deviation principle want to understand is if we take certain value that is away from 0, for example, y, and understand the probability of the terminal position to stay around y. Of course, this probability will decay to 0 as you send epsilon goes to 0. But we want to understand how fast does this probability decay in this asymptotic. And more generally, we can ask the question, how about we understand this entire random trajectory to stay around a certain path that might not be constant 0, but just some continuous path. So this question was answered by Schroeder in 1966. And the result tells us that just pick a fixed path, gamma, okay, a continuous path. And when you look at the probability that this Brownian trajectory stay around this gamma, and this probability will decay exponentially as you let epsilon goes to 0. So there are two terms on the exponent. The first one here is this 1 over epsilon, and it's called the speed. You can see this thing goes to infinity. So the speed does not depend on, which path you choose, okay? And there is something that does depend on gamma, which is called the rate function. It tells you, okay, although we have these paths that are, or unlikely some exponential decay behind, but the rate function will tell you if you compare each other, which one is more likely. Okay, and the rate function takes this specific form of this 1/2 integral of the square root of derivative. This just comes from the tail of the Gaussian random variable and the independent structure in the Brownian motion of the increment. Okay, and H1 is just the function that the function space that make this integral finite. Okay, so you might wonder what does approximation means. So there's a precise meaning of the large deviation principle behind. This approximation means, okay, the trajectory stays around this gamma, but we need to introduce some topology. So in this case, we equip the space with some uniform topology. And when we say it satisfies the large deviation principle, it just means, again, you can just think of this probability. It can be approximated by, so here I take the logarithm, but when you raise to exponential, it's exactly this form. Okay.
Excuse me. Just one question. We know the Brownian motion is not smooth. And now here it looks like when gamma is essentially C1, yes, H1 behaves better than the irregular one. So intuitively.
So what it tells you is, okay, the Brownian motion, it's not smooth, but it stays close around some smooth function. And when we are measuring in the sense of large deviation principle, these, okay, not very smooth function, these H1 functions, they are the correct path to look at where the Brownian motion stays around. If you look at each realization, it's not true. But when you look at where the Brownian motion stays around the path, then these are the functions that you should look at. Okay, so now we have studied the probability of the rare event. So now we can ask the second question, what's the consequence after a rare event happens? So what we do is we fix some value y that is real. And I'm going to condition on some rare event, so root epsilon. So the terminal position that is equal to y. This is rare because typically this thing will just go to 0. And want to understand what is the shape of this trajectory. Okay, so what this trajectory stays around as epsilon goes to 0. So you can see there's some simulation that tell you these colored trajectories, which are the sample from the simulation, all stays around this straight line from the origin to 1y. So it tells you the limit shape should be a straight line. And how can we understand this question mathematically? So remember, we have a large deviation principle. And again, the large deviation principle we have compares the likelihood of each path using the rate function. The paths that have the smaller rate function is more likely. So when we understand which one is the most likely one, we should consider the path gamma that minimize my rate function. Okay, but here, of course, I need to consider some condition, and because I'm doing this conditioning, I fixed my Brownian path to end at y, so I need to consider all the paths that start from the origin and end at this position, and then try to understand what is the minimizer of this quantity. Okay, so the Brownian motion only has only have a time arrival.
Excuse me.
Yeah.
So use your large deviation principle, that result holds true under the conditions?
Yes. Yes.
Okay.
Yeah, so in the conditional setting, when you look at the rate function, it's indeed so this limit shape is a minimizer of the rate function when you impose this condition. These explanations are equivalent to each other. Yeah, so we want to understand some process that not only have a time arrival, but also have a space arrival. And the class of examples are given by this random interface growth model, and the space-time process is given by the height function of it. So the background is I have some interface that is growing, so there's a time arrival, and my interface, there is a space variable, so I'm measuring the height at different location. Okay, so this random interface, they appears everywhere in the nature. For example, in California, you can see there's a lot of wildfire and it's propagating. So the burned area and unburned area, there is some interface and it's moving. So you can think of it as a growing interface. And so this is something in biology. So cells may want to join together to form some aggregation. And as time evolves, this cluster will become larger and larger. So you can see there are some interfaces growing. And on the right-hand side, there's some mathematical model that models this type of interface growth called the Adams model, where you just start something from the origin and the neighboring points in the lattice will join the origin, forming a cluster, and then it attracts the neighboring lattice to make the cluster larger and larger. Okay. So another example is the Tetris. So when you play the Tetris and can think of the height function of it is growing the top location. Okay, so it's a growing interface. And you can, this is not just something from the game, but actually something you can observe in the physics. So here this simulation is about the coffee particle. So when we have a coffee that drop, okay, the coffee spilled and fall on the paper, then the coffee drop becomes flatten, and you will see a coffee ring. And the reason why you'll see a coffee ring is these particles, these coffee particles, you will move towards the boundary of the coffee ring. And when you look at what happens at the boundary, it's some structure that is very similar to the Tetris growth. So the question is, can we write down some equation that models these random interface growth at the same time, capture the important structure behind? So Gaudreau and Zhang in 1986, they proposed this stochastic partial differential equation, okay, called KPZ equation. And there are three terms, and there is a meaning for each of them. So when you want to model this interface growth by writing down equation, you first, what you can write down is a heat equation. Because for heat equation, the Laplacian tells you that as time evolves, even if you start from some interface that is very rough, things are going to smooth out, okay? And because we have some randomness, and the randomness should be everywhere in my space-time domain, so it makes sense to add some noise term. And the noise here is called the space-time white noise. But how you understand it, it's not something that is point-wisely well-defined. It's a Gaussian field, and the correlation function is given by the Dirac delta function. You can think of it as you put ID random variables on the lattice, and then you zoom out, and then things becomes noise. That's what I mean by the space-time white noise. And the most important term here is this term, because if you only consider the first term and third term on the right-hand side, what you're going to observe is again, some Gaussian field, okay? But there are a lot of physical experiment that tells you when you look at the fluctuation of this random growing interface, the fluctuation is not Gaussian. So this second term, it captures one very important property in this random interface growth. It tells you that this interface, it grows in the normal direction. That's what we call the lateral growth. So it will not just be something like going up, it will do something like spanning out. So this is okay, what I mean by growing in the normal direction. And when things grow in the normal direction, then when you look at some interface and things grow in the normal direction, and here I have the slope, which is the partial derivative of h. So if I have a unit growth in the normal direction, then when you look at the height, because we are measuring the height using the vertical coordinate, when you measure the height, it will grow 1/1 plus partial x h squared. Okay, so this suggests you should put something like this in the equation. If you just put this term, it will lead the equation be somewhat hard to track. So what we do is Okay, actually what they do is they say, okay, what we are going to do is just to do some Taylor expansion. Okay, and this is where this second order terms appears because the constant term can be easily absorbed in the KPZ equation by some transformation. Okay, so this term is a non-trivial term that appears. Okay, that's how this KPZ equation comes up. And then actually the simulation tells you indeed when you look at the KPZ equation, the fluctuation of the interface and order of it is consistent with the experiment. Okay, so it is indeed a nice model to for the random interface. So mathematically, we want to understand how to make sense of the solution theory. And there's a problem here because what happens is when you look at the KPZ equation, spatially it will behave like a Brownian motion. And when you try to understand this equation in the classical sense, then when you take the partial derivative in x, what you get is a distribution. And then it doesn't make sense what we mean by squaring a distribution at here. So one way, actually the first way people try to make sense of the solution theory is carried out by Gaudreau and later the work of Bertini and Giacomi. What they study is a different equation called the stochastic heat equation. So it's a linear equation. You only have a heat equation part plus some noisy part. And the noisy part is given by this Z multiplied by the space-time white noise. Okay. And the relation between the solution to the KPZ and the stochastic heat equation are linked by this half-cone transform. And the reason behind is, okay, if you just assume everything that is understand pointwisely, so these Z and C, they are all smooth function, then you take the logarithm of Z, you can just verify this H will satisfy the KPZ equation pointwisely. Okay, so what they propose is you just look at the solution to the stochastic heat equation and how you understand it, you can write it in the Duhamel form, write it into an integral equation. Then the integral against the space-time white noise can be understood as a stochastic integral. And things all behave very nicely. You have existence, uniqueness, and very nice property about the equation. So to study the KPZ equation, it's the same of first studying the stochastic heat equation, then take the logarithm. And for the stochastic heat equation, the solution has also have a different separation, and you can view it as the partition function of a directed polymer. So what I mean is you apply Feynman-Katz formula to solve this equation, and then you will have some Brownian motion that comes from this Laplacian running in some random environment given by this noise. And the Brownian motion, okay, actually it's running backward. It starts from time t and going back to 0, okay? And pick up the value. Of course, when you look at the stochastic heat equation, you start it from some initial data at time 0. So you pick up some value on the initial data and then also pick up some value from the noise, compute the expectation. So you need to notice that this expectation is only acting on the Brownian motion. So the randomness of C is still there. Okay. So that's how we define the partition function of some directed polymer. And in that language, when you take the logarithm, H becomes the free energy of the polymer model. Okay, so it is well known that when you look at the KPZ equation, let's just look at the height function as 0. And I'm going to let time go to infinity. So it turns out that you will have some linear growth, okay? And when you look at the fluctuation, you will have the order t to the power 1/3, and the fluctuation is given by this Tracy-Wyndham distribution that first appears in the random matrix theory, which characterizes the fluctuation of the largest eigenvalue of some random matrix. And this was first proved by Amir Cohen-Costel, and also their important contribution by these three works, which is on the physics side. So unlike the Gaussian random variable, this Tracy Wyndham distribution has asymmetric tail behavior. So when you look at the lower tail, which means this chi function is extremely small, then you will see this cubic tail decay. While when you look at the upper tail, you will see this 3/2 tail exponent. And it was first predicted in the work of Koloklov and Korshunov in 2007. They say that when you look at this lower tail behavior, and you do not let time go to infinity to study the fluctuation limit, but instead you look at the finite time, what you're going to see is a different tail exponent that you do not observe from the fluctuation. And the tail exponent here is given by 5/2. Okay. While on the other hand, there's no such transitions. Tail is always given by 3/2 exponent. So this 5/2 tail exponent have received a lot of interest recently from the side of stochastic PD and the integrable probability. And it was first rigorously proved in the work of Corwin and Gosal using method of integrable probability. And there has been two approaches till now. The first approach of generally understanding the tail behavior or large deviation of this KPZ equation is to actually you can characterize when you start the KPZ equation from some special initial condition, you can characterize this 1-point probability distribution using some exact formula. And this formula is very explicit, but also on the other hand, very complicated. So when you let time goes to infinity, you need to do some asymptotic analysis on this formula. And there's a lot of work on this side using the exact formula to understand what happens in the tail of the KPZ. And there's a different flow of work using so-called weak noise theory. And the logic behind is if we want to understand the probability of this H stay around this lambda. And in general, this lambda is, for example, very negative or very positive. So this probably have certain decay and it's unlikely. So we want to understand first the space-time trajectory that will make my value behave unlikely and use that information to study the tail. And actually, this allows you to not only understand the 1-point behavior, but also understand the entire space-time trajectory of the KPZ equation, which might be hard from the integrable probability side, okay? Although it provides very explicit formula. So there are many physics works in this direction, and recently we have derived the mathematically rigorous approach that I will describe later. And so what we are going to consider is the KPZ equation with a small parameter epsilon, okay? And we are going to multiply the noise by this root epsilon. So we make the noise become weaker and weaker. That's why we call this to be the weak noise scaling. And mathematically, this formalism of small noise perturbation or this weak noise setting is known by the name of Freilin and Wenzel when they first studied this system stochastic differential equation that driven by this diffusion with small noise perturbation. And to understand the space-time trajectory, the behavior of it, the first step is to establish a large deviation principle as what people did for the Brownian motion. Okay, and this is what we're going to do, but I want to tell you that we're not the first one to understand the large deviation principle for stochastic PD. Actually, there are a group of works, but what we're going to study is this KPZ equation, and it's not something that is well posed. So we're going we use some method that is different from this line of work. And here is the first result. So basically, what I want to tell you is the KPZ equation. Okay, what happens is when you let the noise vanishing, then sorry. When you let the noise vanishing, then the trajectory will just become closer and closer to some deterministic path. And the deterministic path is given by you drop the noise and solve the PD. But when you ask what is the probability of the solution stay around some other path, G, that I fix, and this probability will decay exponentially with the speed 1 over epsilon. And the important thing to understand is the rate function at here. So I will just tell you what this rate function look informally. So you can compute this rate function by computing this integral, okay? And what inside this problem parentheses represent is when you plug in the KP's equation, this is, when you do the subtraction, this is what you get from the noise. And when you look at the noise, the large deviation rate function is given by something like the L2 norm. That's why the rate function of the KP's equation have some form like this. Okay, there's some small problem because what we're looking at is the space of continuous function. So when you have the space of continuous function, how you make sense of taking the derivative when you do not have differentiability. So what we actually do is you first represent the thing inside by rho. So in the end, the rate function become this L2 norm. But on the other hand, we try to solve this KP's equation, and we require the solution is equal to G. Okay, and this can resolve this issue. All right. So, and what we're going to study when you look at the KP's equation, and now we are going to explain how, where this 5-half tail exponent show up. And we're going to restrict ourselves to some special initial condition. Although our result does work for some other initial condition, but I'm going to focus on that. So this initial condition corresponds to you let F starts from this log of Dirac delta initial condition. Of course, when you take the log of Dirac delta, it doesn't quite make sense. But at the level of the stochastic heat equation, what I mean is you solve the stochastic heat equation start from this Dirac delta, which means you're looking at the fundamental solution of it. Okay, and why we call this to be the narrow edge, it means, okay, when you let time goes to 0, what the solution behave of the stochastic heat equation is just given by this heat equation part. So you get a heat kernel, and you take the logarithm, you will get this problem. And in particular, when you let time goes to 0, this problem will become narrower and narrower. That's why we call this to be a narrow edge. And it's a natural initial condition because the KP's equation, what you can do is you can discretize it. Actually, it has, it can be realized as the pre-limits of interacting particle systems. So the narrow edge initial condition comes from when you think of interacting particle system is on one side you have packed particles, on the other side you have no particles. This is what it corresponds to in the discrete setting. And what we show is, again, when you look at this KP's equation under this weak noise scaling, as you let epsilon goes to 0, now you only look at the 1-point setting, okay, you will get some rate function. The rate function will take some variational form, but I'm not going to show you. The important thing is if you let lambda goes to -infinity, which is the lower tail regime, you will see this 5-half tail exponent. And this result is, it has been predicted by this physics working in this literature of the weak noise theory. And what we done is to prove it in a rigorous way. And on the other hand, when let lambda goes to +infinity, you will see a different tail exponent. So actually we did something more than understanding the 1-point behavior. What we'll actually do is, okay, here I'm looking at the probability of some rare event. This value stay around this lambda. And what we do is now we are going to condition on some rare event is exactly let this value at 1, 0 equal to lambda. And I let lambda goes, let the noise goes to 0 and let this value we're conditioning either goes to infinity or minus infinity. It's exactly the same regime where we have studied the tail, okay? Go very negative or go very positive. And we can show that the space-time trajectory will converge to some deterministic path. And okay, I will tell you what these paths is, but they're explicit and not hard to describe. So now I can tell you where this 5/2 tail exponent comes from. Because what you have observed from here, for example, when I let lambda goes to minus infinity, my H epsilon itself is not something of order 1, but you have to impose this scaling to make it some order 1 object. This means that when you look at the rate function, okay, this is the 1-point version of it, but there is also a functional version of it. When you look at the function g, in the end, you're looking at the L2 norm, the square of the L2 norm of it. So where this 5/2 tail exponent comes from, it comes from the fact that you impose this scaling and compute the square of the L2 norm of this function. So under this scaling, when you compute the square of the L2 norm, you can factor out this lambda to the power -2. And you can also factor out this lambda to the power -1/2, which is by a change of variable. So 2 plus 1/2 is 5/2. So this tells you where the 5/2 tail exponent comes from. But you might wonder, here, the 5/2 tail exponent corresponds to the regime of lambda goes to minus infinity. So we should also expect, because you have the same scaling in lambda goes to plus infinity, we should also expect the 5/2 tail exponent in this regime, but instead we get a 3/2 tail exponent. So what happens is there's actually some degeneration happens, something that is vanishing and will make the tail exponent become smaller. Okay. Any question about here? Okay, so how we study this question? So in the end, our approach is a combination from the probability side using the tool of stochastic analysis and the large deviation tool. And on the other hand, using this PD approach. So where does this PD arise? Remember, this limit shape we want to understand. So consequence after event happens, it corresponds to the minimizer of some variational problem. Think of the Brownian motion example that I have showed you. So here it's something similar. When you just let the noise, when you just let the noise goes to 0 with a fixed lambda, okay? Then the shape actually, okay, I'm just going to let lambda to be 1 because for general lambda, there will be some scaling. So this limiting shape, it's actually the minimizer of the rate function of this large deviation of the KPZ equation. Okay. Of course, with certain condition at the terminal location. So when you want to find the minimizer, so now you look at this rate function and you want to understand what is the minimizer of the rate function. What we're going to do is we can do some calculus variation. It's the same as when you want to understand where is the minimizer of the one variable function. You just take the derivative, find the critical point. Here, I'm going to do some infinite dimensional version of that. And what you can derive is some equation. Actually, usually from this kind of expression, you will get a second order Lagrange equation. But what I'm going to do is write it as some first order Hamilton equation. Remember here, I will just let rho to denote this expression. And what you derive from the Lagrange equation is exactly this expression. And curiously, things coincides with, okay, these equations, they're actually the forward-backward equation, forward-backward PD. And this coincides with an important equation in the mean field games called the mean field equation, where the first equation tells you, okay, how the value function of certain stochastic control problem behave. And the second question describes the density of certain stochastic differential equation given by the control. Okay. So what we want to understand is actually it's not just for when you take lambda equal to 1, you will have this equation. Remember, we want to understand the asymptotic behavior of H lambda. So each H lambda will satisfy the equation. And I want to understand what asymptotic limit of this PD behavior.
Excuse me, what's the rho again? Their rho?
So rho, you can think of it. So this is exactly a deterministic version of the KPZ equation. What rho it represents is a certain realization of the noise. But here you can, what I mean is you can just think of these two equations as one equation by plugging the rho with the left hand side. I just write it in this way to make it simpler. Does that answer the question?
Is there an intuitive explanation of the connection with the mean field against us? Just mathematically it turns out.
No, this is something that people are still curious about why there are the mean field equation comes from the KPZ equation. But my understanding is currently it looks like some coincidence happens.
Oh, by the way, in the previous slide you have the two limits, yes? The previous
Right.
slide.
Right. So
can you switch the order? I guess not.
this is a good question. So the result only holds when you have this kind. You first take the noise goes to 0, then you let lambda goes to plus infinity. Things should hold when you let lambda and epsilon both tends to asymptotic limit with certain speed, but this is something we don't know how to prove. How many time do I have?
Maybe 15 to 20 minutes.
Okay. So what we're going to study is the asymptotic behavior of this H lambda, and they will satisfy some rescaled version of this Hamiltonian PDE. And the only thing that you will see in this rescaling is the second order coefficient. Okay, and of course, again, there is some forward backward condition at here that I did not show you. So from the PD perspective, what we're going to do if we want to understand the asymptotic limit of these equations, the solution of these equations. So in particular, as lambda goes to minus infinity, this is what the physics literature do is they propose, okay, the limit of this H lambda should be the solution of the PD when you drop the second order term. Because when you let lambda goes to minus infinity, this coefficient all goes to 0. So you should, these terms should vanish in the end. If H lambda and rho lambda is something of order 1, these terms should disappear. So you want to solve the limiting first order equation, which looks simpler. And what they did is they apply some series expansion. What they do is they expand this rho and H into series of X, polynomial expansion of X. And in front of each term, you will have a coefficient as a function of P. Then you just plug in the series expansion to this PDE, you solve it matching the coefficient, you can find some solution. And the solution they find, okay, the physicists have certain sense what is the correct solution to look at is this second order, this quadratic function in X with certain, explicit coefficient as a function of T, something that is that can be determined for each value of T. And plus means you only take the positive part of it. So this is something they propose to be the physical solution in the lambda goes to minus infinity limit. You might ask, okay, again, when lambda goes to plus infinity limit, it seems there's nothing different. The second order term also goes to 0. The things that happens behind is this initial and terminal condition, they have different behaviors that will make the solution become different. So what we showed is that, okay, we have So the limit of this PD has been proposed by the physics work, but how about the convergence? So what we show is that this pre-limit actually converges to the limiting equation in the sense of L2 norm. It is usually most convenient to first understand rho than H, because as we will see, when you remove this second order term, you have this Hamilton equation, and there are infinitely many solutions of it. So again, you need to understand which one is the correct solution. So we show that there is some L2 convergence. So this tells you what the limit of this H lambda look like. Because what you have observed is this H lambda and rho lambda, they are linked by this PD. So if I understand the limit of rho lambda, I should be able to solve, okay, even in the pre-limit, I understand what is rho lambda, I should be able to understand what is H lambda. So there is actually a Feynman-Katz representation that can represent the solution of H in terms of this potential rho. It's similar as what you see the Brownian motion evolve in the space-time white noise, and you compute the expectation of it. The only difference is now the space-time white noise is replaced by this potential. And so I want to understand what is the asymptotic limit as lambda goes to minus infinity. So actually, the limit, there are two steps. First step is at more heuristic level. You can say, okay, the limit should just be, you replace this rho lambda by its limit. Then you do the same computation. And this computation is standard. It's some general philosophy energy entropy computation, actually also the content of Varadhan's lemma. What you're going to do is, okay, we have some Brownian motion evolving the potential, and I want to understand what is this expectation behave, in particular when lambda goes to minus infinity. So this Brownian motion, you will stay around some shape. It will stay around some trajectory given by gamma, okay? And when you stay around this trajectory given by gamma, the value from the exponent is just given by this integral. But on the other hand, this Brownian motion turns out to have very small diffusive parameter. So in general, it will just become like a straight line. So you will take certain probability for your Brownian motion to behave like a path gamma. And the probability actually, the decay is characterized by this rate function you see at the beginning. So you want to maximize this combination of energy and entropy combination to figure out what is the optimal path, and then you compute the value, it should be the limit, okay? But on the other hand, this is only true when we justify we can indeed replace this rho lambda by this L2 limit. In general, it's not true that we will have some L2 convergence, you can replace the pre-limit by the limit. There are counterexamples. But in our case, indeed, we showed in this work together with Li-Cheng Tsai, we showed that you can do this replacement. So you can show this convergence. And actually, we have a very explicit characterization of this optimizer gamma. When you look at the value of the solution at certain t and x, then you want to optimize the trajectory that connecting the origin and tx. So what is the optimized trajectory? Actually, it's something that can be described very explicitly. So there is some oval, where this LT function is something of we have seen in the potential. So inside this oval, these optimizers, they will just flow, by a scalar times this boundary. Okay, but outside the trajectory, these optimal gamma will just behave like straight lines. So for each terminal position, you can have a unique geodesical optimizer connect from the origin to that position, except at this terminal position where you're doing conditioning. So something weird happened. You have infinite many optimal gamma that connect the origin to the terminal position. Okay, so this explains what happens in the the lower tail situation, when you condition the value, condition the 1 point value at 1, 0 to be lambda, and lambda goes to minus infinity. Understand what the trajectory of the KPZ equation behave. So on the other hand, you can also let this lambda to be very large. And again, these physics works, they predict actually, in this case, things are quite simple. This rho lambda, this representative of noise, it will just vanish. It will just converge to 0. Then you want to understand what happens to the solution.
Excuse me, I forgot. Did you mention it on for fixed lambda? Is that the FDS? I mean, for the backward assistance, the solution is unique or not?
For the fixed lambda, the solution should exist and is unique. Yeah, I will talk a bit about that for the fixed lambda. But here, let's first look at the asymptotic lambda situation. So again, in this case, since this rho lambda, now it just vanished. So when you look at the PDE, you just have something that is vanishing here, and something is also vanishing here. So it tells you that the limiting behavior of this KPZ trajectory, it should just solve this equation. It's the integral form of the Burger's equation with some specific initial condition. But the problem is, okay, you need to understand which solution should represent this H star. Because should we look at the entropy solution, which is the physical solution just like this term, or should we look at the weak solution? If we look at the weak solution, there are infinitely many of them. So the result is, because we are doing some conditioning on some rare event, so the limiting behavior should not be this entropy solution. It will instead be something that is, it's a non-entropic solution that is given by this explicit form. Okay, and the idea behind to show this is again to understand what is asymptotic behavior of rho lambda. But now you, instead of just look at the order 1 scaling where things goes to 0, you need to zoom in around the position x equal to 0. Then you will see something non-trivial happen, and which actually becomes some time independent function. Then you can again use the Feynman-Cass formula, this energy entropy type of argument, to show this function. This is where this expression comes from. So as what you have asked, when you look at the pre-limit, so here I just take lambda to be 1, but actually things works for every lambda. You might wonder, okay, at the pre-limit, can we just find out what is solution? And then if we want to study asymptotic, then just do asymptotic analysis. Actually, this was proposed in the physics works by Yana, Kamenev, and Merson to do this transform. The first transform looks like a Hofkold transform. The second one is slightly different. You will just change your equation to something more like heat equation. Okay, and it's actually something called the imaginary time cubic nonlinear Schrodinger equation. And turns out that with specific initial and the terminal condition, these PDEs, they're integrable. Integrable means there is certain method that can solve this equation explicitly. Although this is a nonlinear equation, we know in general when we have heat equation, the linear part of it, we can solve it using Fourier transform. But for the nonlinear part of it, there is some generalization of Fourier transform called the inverse scattering method, which is much more involved, but can tell you what the solution looked like. And actually, this was done in the physics work by Krajenbrink and Ledoucet, and also later by the work of Li-Cheng Tsai, where they proved part of the work in the rigorous way. And they showed that this P and Q, so equivalently this H and rho, they admit some explicit but rather complicated formula. Okay, but something nice, at least we have some explicit description of what is the shape of the equation at finite lambda situation. But extracting these asymptotics from this complicated formula, it's more like what they do in the integrable probability, rigorously remains open.
About 5 minutes. Just
okay. Yeah.
So for Q, we know the terminal condition, but for P, we don't know the initial.
For P, so it's better to look at this equation where this H have some initial condition and rho has some terminal condition.
H has initial, H has terminal.
Okay, H is the KPZ equation. We started from some initial condition.
Okay.
Yeah, and rho is actually, you get the terminal condition because we're conditioning the value of H at time 1. This is from what you're doing in calculus variation.
Yeah, but then Q has an initial, but P we don't have terminal.
Yeah. So Q has some initial condition, but P. Yep. But in the end, you can still use certain method to formulate this in some forward-backward equation, and it's like solving things in the inverse way to figure out what the correct condition is to solve this equation. Yeah. Okay. So now the general question I want to talk about in the end is, can we understand the behavior? So what we have studied is when we observe the trajectory of the KPZ, only have one snapshot. We observe the value at one point. And I want to understand what is the space-time trajectory look like. This is what I have talked about. So I want to understand, can I at least generalize this picture to, if I have more information, I have 2-point information or multi-point information, can I have a better understanding of these trajectories? So this corresponds to conditioning at the multi-point situation. And to understand that, I'm just going to give you a different explanation where this limit shape appears. So as we have seen, it solves this PDE, but it's not the entropy solution when you look at the forward setting. Actually, when you look at the characteristic lines, it's something that is going out from something in the middle. So this is why we call it non-physical, because the characteristic line cannot go from somewhere in the middle. But when you turn the picture backward, things are going together. So, and they form a shock. Then in this case, it's indeed the entropy solution when you solve this equation from time 1 backward from certain initial condition. And this initial condition can be explained by some Brownian property of the KPZ equation, which tells you that typically the shape of the KPZ equation, if it's a parabola, and I have conditioned the value of it to be large, then what the KPZ will behave is just like you put a rubber band on this parabola, and it gets pulled up, at certain tangent direction. And it's exactly what the equation looked like at time 1. Okay, so this maybe it's the final picture. And actually the conjecture is, if we can actually generalize this to the multi-point situation, where we condition multi-points value lie on this parabola and understand the limiting shape of the KPZ equation, it turns out that what people should expect is, again, the limit shape should be given by, you solve this equation from backward with certain initial condition, again, from putting this rubber band on the parabola and make it pass through these points, and then solve it using the characteristic method. And now you will see these shocks, they have a merging structure, they'll go back to 0. And actually, we didn't really prove this in this in the setting I talked about before in the weak noise, but in some other setting, we do prove this is the situation with some help using the Feynman-Katz formula. And I just want to stop.
Question?